Hello, everyone. Welcome to the next session at the Shift Room. We're now having our second speaker, Arjun Manjunatha, with the title of Leveraging Generative Adversarial Networks for Building Synthetic Data. He's currently working as a machine learning engineer at Sention. So let's welcome him.
Thank you for the introduction. I hope you guys had a wonderful journey over here. It's a Saturday morning. I appreciate you being here to learn about GANs. I'm going to be giving you an overview of GANs and how you can leverage GANs to build synthetic data. A little bit about myself. I am a machine learning engineer. Like the rest of you, I teach machines how to predict, classify, and in this case, generate data. I work at a startup called Sention. Basically, we are a battery diagnostic company. We scan batteries and then analyze the data and then give insights on how the battery is performing. Godfather of AI said GANs have been the best thing that has happened to deep learning. I may have paraphrased the last part of the code to fit my preference, but you get the point. Yeah, why do we need generative AI? Generative AI is capable of building large language models, generating images, videos. So OpenAI is working on generating videos. But there are other use cases as well. You can generate synthetic data. You can extract features, which we'll see in a later slide. And in real life, we know that the data sets are often imbalanced, and we can solve this problem using generative AI as well. How do we use GAN? We were trying to build RNNs to predict the life cycle of a battery, but we were working with a very small data set, so we had to leverage GANs in order to build a bigger data set and build a more robust RNN model to predict the life cycle of the battery. That's how we used generative AI at Sention. Let's try to understand GAN at a very high level. For instance, I am trying to learn how to cook, that's me, and my roommate is a chef, he's a professional chef, and we'll drag another roommate to be our taster. Initially, I am bad at cooking, so my roommate taster won't be able to differentiate my cooking and, he'll be able to differentiate my cooking and my chef's cooking. But then he gives me feedback on that there was too much salt, it was undercooked, overcooked, and I keep track of this information, and I understand what makes a good dish a good dish. So with every iteration, I try to learn the distributions. After several iterations and a very expensive grocery bill, I am able to cook as good as my roommate chef. And over here, I am the generator, and he's the discriminator. We'll see that in the next slide. Going in a little bit deeper, generator's job is to generate data, and discriminator's job is to make sure, to classify the generated data, whether it's real or fake. Generator takes in random points, and then it classifies whether it was real or was fake. Yeah, the boring part. Objective function. The job of the discriminator is to label real data as 1, and generated data as 0. And the generator's job is to fool the discriminator in order to thinking that the data was real. A little bit of math derivation. I didn't want to bore you, so I didn't put it there. But it looks very close to binary cross entropy, if you're familiar with that loss function. And this is your analyzed loss function. How do we train GANs? Initially, we labeled the generated data as 0, and we labeled the real data as 1. And then we only trained discriminator to identify real data and fake data. And then once we finish that step, the next step is to not label the data and then feed in both real and fake data to discriminator, and then give that feedback back to the generator for it to learn how to create fake data. Fake data. Let's look at an example. Suppose we are trying to predict, build a data set for X squared. We have one layer, multi-layer perceptron, and for generator, and then discriminator. And then, like we talked in the previous slide, the first step is to get the generated data, label those as 1, and the discriminator gets trained in the first iteration, the backpropagation. With the help of backpropagation, the discriminator understands what it is doing wrong, and then in the next step, we do the same thing for generator. This is how it would look like when we are training it. Initially, this won't be the case every every single time. It happens randomly, but it tries to learn the distribution of the data. Yeah, after 8,000 epochs, you can see that it's sort of settling into that curve. And then after 10,000 epochs, there are still some points which lie outside of the curve. In real, you could still go train for 20,000 epochs, and you would get a perfect curve. But in real life, we always sort of have this kind of thing going on. So if we were to stop there, how the data that we generated was authentic? The best way to do that is to have someone with domain knowledge, so they will understand whether the generated data is good enough or bad, and then you can compare the distributions of the real generated data, and you can also use some statistical tests to see how well the generated data is compared to the real data. This is also some of the other metrics. These are usually used in computer vision problems to compare how good the generated and the fake images were. None of these people are real. These are all generated by style GANs. If you're working on computer vision problems, it's a very good tool to leverage, build a variety of data to build more robust deep learning model. This is an example of how you can use feature extraction. This is a slightly different architecture than GAN. You have an encoder which maps the data into a lower dimension space, and then lower dimension space, and then you have a decoder which takes the lower dimension space and reconstructs it back to the original data. You can use this latent space to do clustering or multi-class classifying. Sky's the limit, basically. Yeah, but with everything else, there's some challenges with GAN. One of the biggest challenges is mode collapse. For instance, in the cooking example, if I knew how to make good pasta and my roommate chef knew how to make good pasta, my other roommate will never be able to tell the difference, and I won't learn all the other dishes. So I stick to that one dish because my job is just to be good at fooling discriminator. You have the other case as well, where classifying is usually a simpler problem compared to generating data. So when you have a really strong discriminator, the generator doesn't have the chance to learn all the data distribution and generate good data. We looked at the loss function. The discriminator always tells whether the generated data was real or fake, but it never tells by how much was it fake. So this information would be helpful to understand how generators are learning. Tuning hyperparameters is hard enough for one model, but when there are two models competing against each other, it is really hard. It's not impossible, it's just a challenge. Yeah, these are some of the other generative networks. These are usually built for the challenges we talked in the previous slide. You have WGAN, which has a different type of loss function, which tells the generator by how much does it need to improve in order to generate real data. You have conditional GAN. Usually we don't have the control over what the generator generates, but with conditional GAN, we can send in an additional input and we can get what you want, generate what you want. DC GAN, style GAN, these are again used in computer vision. Muse GAN is used for audio and generating music. If you've seen pictures of dogs wearing spacesuits or snowboarding, these are usually generated by stable diffusion. Transformers, in large language models, every large language models, the underlying architecture is transformers. Yeah, thank you. I'm open to questions. Thanks for listening. Yeah.
So a couple of questions.
Sorry. Can you just tweet?
So a couple of questions. I'll start off with the very simple one, which is you were talking just now about Muse Gen, and you gave the example of it can be used with music. Could it be used with other types of audio as well, such as maybe like commentary, for example? Mm-hmm. And also if I want to kind of get more into this whole generating synthetic data using Gen AI, where would you say is a good place to kind of start in terms of experimenting? Would that be a website or trying to solve a problem or something?
So if you're trying to generate audio,
yeah.
I'm not familiar with how you tokenize audio.
Yeah.
So if you figure out how you tokenize audio, you can leverage the same architecture they use for images. Not images, time series data. Images, they use convolution. Time series, they probably use RNNs. So you just need to know how to tokenize the data for you in order to feed it. I think the rest of the thing still holds true, the architecture, the loss function. And then MuseGAN, I think they have a method to tokenize audio.
Okay. Thank you very much for
No
that.
worries.
Any other questions?
Hi. So you were mentioning that you didn't want to overtrain your discriminator.
Sorry?
But so what would be your minimum and maximum thresholds for your discriminator so that you're having an appropriate GAN for whatever your purposes are?
That's kind of a trial and error situation. But one thing to keep in mind is to train generator and then train discriminator to make it balanced. Not train the entire generator at one time and then the discriminator at one time and then the generator. You have to take it step by step. You generate it for like 10 iterations. You train the discriminator for 10 iterations. You train the generator for 10 iterations. If you're having that problem, you can use, it's overfitting for discriminator, you can use other methods like regularization, normalization to make sure that it's not overfitting, and then you're dropping those neurons in the discriminator for giving a chance to generator to learn.
Any other questions?
Thank you for the introduction. Could you talk a little bit more about how you use this at Sention?
Yeah, so we were trying to build an RNN which could predict the life cycle of a battery, but then we were working. I'm not allowed to say how big of a data set we were working on, but we were working on a small data set, and then all my colleagues were they've been working in batteries their whole life, so they know the generated data, whether it's real or fake, does it make sense. So we used generative AI, see if we could use it, and then it worked out well. So we generated data, and then we had this task wherein one of our other colleagues had the task of saying whether it was real or fake, and then we tested how good of a data set it was. Then we used it for RNNs.
Thank you.
No worries.
Just a follow-up on the previous question, how do you scale this human judgment on like if the data is truthful or not, like realistic or not?
Yeah, you need someone with domain knowledge. They have seen battery data their whole life, and they can spot fake. It's something like how you can fake a fake Nike T-shirt from a real Nike T-shirt. If you wear Nike your whole life, you can spot, oh, yeah, that's the fake Nike shoes. It's something that when you have the domain knowledge, it helps. Yeah.
Yeah, but when you are facing a very large data set or you need to generate a lot of records, do they need to go through one by one?
You can use statistical tests like random sampling and then see how well, and then you can compare the distributions, like the entire data distribution of the real and the fake data, and then see how they fare. You can use other statistical tests that is relevant to your correlation, how different features are correlated. Is it the same for the generated data? Is it the same for real data? How well are these metrics for these two data sets? You will get a rough idea, but there's always a case when the generated data doesn't make any sense, and it's usually not advisable for financial data and healthcare data. Yeah.
Another follow-up question on this. So just to understand the objective of this, why do you need a larger data set? And the main objective for this, you talked about battery diagnosis. So is it like prediction, or is it like classification on whether it's working or not?
It's a time series prediction wherein how would it age after 20 cycles? How would it age after 40 cycles? It's mostly for battery manufacturers. We are trying to aim for them, and then it would help them. They've developed their manufacturer cell. How would it last? Is the electrochemistry good or is it bad? How would it fare after 20 cycles? To give that prediction, we needed RNNs like sequence. So you usually need a big data set for deep learning models. Smaller data doesn't work. So we had to build a data set or go with something much simpler.
Thank you.
Hi. So, because as you just said, deep learning. Sorry, I'm here. Deep learning requires a lot of data. Did you try other types of models before trying to generate synthetic data?
Yeah, but most of them doesn't have context. Like simple machine learning models, they don't have context. They can either classify or predict, but they don't have memory on what's happening in the previous state. Only RNNs have that capability to see, okay, this happened in 20 cycles, this happened in 40 cycles, so this should happen in 80 cycles. So only RNNs have that capability to do that.
No? Okay. Thank you so much. It's been really productive and informative. Thank you all for your attendance. Now there is a break until 11 a.m. The sessions will complete in this room and other rooms. So enjoy your break, network, ask questions. Look out for popcorn in the afternoon and enjoy the day. Thank you.
I could just see